We'll talk even more about dummy variables. They're important, but they are complicated, particularly with lots of interactions and lots of dummy variables. It's got lots of moving parts, so you need to do some work to try to explain all the things that are going on. To explain to your audience, but honestly, also, first, to explain to yourself. When we started with OLS just a couple lectures ago, it seemed straightforward enough. We had a single continuous variable and interpreted the coefficient on it as the slope. When the x variable goes up by 1, the y variable goes up by that coefficient. That predicted amount is relatively simple. But if you have tons of complications and interactions and blah, 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 then it really gets difficult, even for the person doing the regression to understand. Certainly difficult to explain to somebody else that hasn't done all that background work. You've got to think about not just how to get the output from the computer, but also what are the best ways to present all this. This commonly involves joint hypothesis tests. For example, within an interaction term, it's sensible to test whether some set of coefficients are all zero. In giving interpretations, it's often helpful to display some predictions. For example, if somebody's predicted wage, a particular sort of person, particular example, would be predicted to make this wage, somebody else predicted to make that wage. You can get a sense of whether those seem plausible. For example, this is a pretty fearsome looking econometric model here. It says wage is determined by age, sex, educational levels, and then interactions of sex with education. If one of your goals is to impress somebody, then okay, show off that big, ugly, complicated regression. But if you want to help people understand, then maybe show some predictions. For example, a 30-year-old female with an associate's degree would average a certain wage. As you plug in term by term, you start to figure out that it may look rather complicated, but actually a lot of those dummy variables are just going to be zero and drop out of the equation. In the bottom part, I grayed out all those terms that just drop in order to concentrate on a few. That makes it more straightforward to understand what the heck's going on. To remind, and it's worth saying again and again, don't be a dummy about dummies. A single dummy variable is implicitly a comparison between the group with the dummy variable equal to 0 and the group with the dummy variable equal to 1. That implies those groups are each homogeneous to a certain extent. Obviously, that's precisely false. There's an old saying that all models are wrong, but some are useful. This assumption of two groups each being homogeneous is of course wrong, but it may be useful. But it shouldn't be too crazy wrong. For example, you might use a dummy if a person has a high school diploma, which will lump together people who got that regular diploma along with people who got the GED. In the US, that means they did not graduate at the usual time. They dropped out of high school, came back, completed it later. Those two groups, people with a regular diploma and people with a GED, might well have some distinctions in different outcomes. But in other analyses, it could be sensible to bunch them together nevertheless. Wrong, but useful. Now, whether it's reasonable to assume homogeneity may depend on the particular questions being asked. That's even more relevant in understanding a common mistake that people make, putting in one dummy variable but omitting the rest of a set. For example, the whole set of dummies on education. Typically, we have no high school diploma, some college, bachelor's, or advanced degree. If I pick out just one, say the dummy for if they have a high school diploma, then I'm implicitly comparing those with the other group, the people with a dummy variable equal to 0. That other group is a weird combination of those with less schooling than a high school diploma, along with those with more education, which is probably not at all homogeneous. So you need the whole set of dummy variables in that case. Another case where you, the modeler, has a choice is sometimes whether to use a dummy variable or a continuous variable. Obviously, sometimes you don't have a choice. Maybe you only have a dummy variable. For example, the household pulse data doesn't tell you the household income, but rather just a dummy variable for whether it's in a particular range. Other times you have a choice. For example, age. Sometimes it's given. Sometimes it's broken into groups like in the 20s, in the 30s, whatever. or even broader group like Boomer or Gen X or Millennial. You can make a plausible argument that actually everybody gives their age in a bin. Nobody reports they're 34.38 years old. In many surveys, people report their age in numbers ending in 5 or 0. Part of the reason we used polynomial terms for an age was because we believed in a model of wage that delta wage delta age is not constant. That could be alternatively specified with age dummies, where now each age has its own group mean, and the change from 34 to 35 can be completely different from the change from 33 to 34. You might remember learning calculus and worrying about the distinction between left-hand side and right-hand side limits. Now, people can argue about which specification is better. There are other examples where a modeler might have a choice. For example, health outcomes. We might have the person's blood pressure, but also dummy variable if they have high blood pressure. Doing sports analytics, there's a difference between using win-loss or points scored versus points against. The former is binned into dummy variables. The latter is a little closer to a continuous measure. Usually it's better not to throw out information. But there are lots of cases where there are discontinuities, in which case those can be useful in modeling. The person doing the modeling just has to know enough about all these cases. Usually when we have panel data, we get lots more dummies. Hooray! But that means you got to even do more work to get it correct. Panel data is repeated observations over time of multiple units. For example, CPS surveys talk to the same person each month, lots of different people. It's a panel. A cross-section, on the other hand, would have a number of different people or units at one particular time. A time series might have data on one particular unit over multiple times. Panel is a rectangle of data. Lots of observation units and lots of times. For stock market data, the price per day of one stock would be a time series. If I have a whole lot of stocks, maybe the S&P 500, then I have a panel. A company might look at sales in different store locations over time. Now, a repeated cross-section is different. For example, the CPS follows people for 1 year, but not longer. The 2018 CPS is a different group of people than the 2021 CPS. For that, you could say the average wage for a college graduate has changed, but you're not looking at the same people. Pooled sample is basically the same idea. Typically for panel data, though, we'd have two sets of dummy variables, a unit effect and a time effect, which, apologies in advance, notation hell. But it's in the service of trying to add clarity. The T subscript indexes time. The J subscript indexes unit. Every observation of X and Y are a particular date and unit, so we have Y, T, comma, J, which is the output of a particular unit, J, at a time T. And then there are the K different X variables. We'll put K as a superscript, which is not a squared term, a different index. There are multiple X variables. So if Y, T, comma, J equals alpha J, those are the unit fixed effects, plus gamma T, those are the time fixed effects, plus beta 1 X1, different for each T, each J, plus beta 2 X2, sub T, sub J, and so on for all of the K different X variables. Then there's an error term. But note the distinction between the alpha J and the gamma T. The alpha J are the unit fixed effects, which do not change over time, so there's no T index. Whereas the gamma T are the time effects. They're common for every unit, so there's no J subscript. Consider this example. Suppose I'm analyzing data for a business that has multiple stores in different locations. Each column is annual sales for 8 different locations of the same store. There are year effects. There are really strong years where everybody sells a lot. Also, there are really weak years where everybody doesn't sell as much. Those would be the time fixed effects. Then I take account of the locations. There's some locations that are just really good. They're really busy. Every year they do a lot of business. Other locations are a little quieter. They don't get as much traffic. Their sales are not as high. If I wanted to evaluate how different stores are managed, understand that while there are some stores where business is always good because of the location, that's not because they have a good manager. It's just a good location. Similarly, there are some years that are good or bad for every store, and that's not necessarily attributable to a manager. To do the analysis, got to create dummy variables for the years and dummy variables for the units, and then regress y on whatever other x variable, and add these sets of dummy variables for the years and the units. Now, these dummy variables mean we cannot include any x variables that don't vary across the unit. Similarly, cannot include any x variables that don't vary over time because they're fixed effects in each case. Those fixed effects soak up a lot of variation. But the bottom line is dummy variables are, they're a pain, deal with it. But on the other hand, they can be very useful. So you should learn how to interpret them because they will get you a long, long way in a lot of your predictions.